Today we're going to be going over how to do Bode plots. Now I'm sure you all have done Bode plots before, so this should just be a refresher. We're going to be going over two different examples. The first one is going to have 1, 0 and 2 poles, and the second one we're going to be deriving a transfer function from an op-amp and doing the Bode plot for that. So for example 1, we're going to have a transfer function 5 times 10 to the 4th s over s squared plus 505 s plus 2500. So first of all, we're going to want to look at this transfer function and determine all the different poles and zeros from it. So we have 1s up top, and because there's nothing being added to it, we know this is an s at the origin. And then we have 2 poles down bottom, and these poles aren't going to be at the origin because you see they're in this quadratic form, and there's a term being added to it here without any s. So now we're going to factor out this term. So we're going to get HCS equals 5 times 10 to the 4th still, times S over S plus 5 times S plus 500. So from this, we can get everything we need to draw Bode plots. So the gain, K, we can just get by doing 5 times 10 to the 4th divided by 2500. Alternatively, we could do 5 times 10 to the 4th divided by 5 divided by 500. You get the same value. And this value is 20. So we know our k is 20. We know we have a 0 at the origin. I just say 0. We have 2 poles at 5 and 500. So this is all the information that we need. These are both simple poles. They're not quadratic. If they were imaginary poles, they would be 2 right on top of each other, and we'd have to do slightly different stuff with that. You shouldn't come across any of those. If you do, you can pretty much just do the same thing, and it's just 2 poles at the same location. So let's get to drawing the Bode plot. So the Bode plot is going to have the magnitude of h of s on this axis. This is going to be in dB. And it's going to have the frequency on the x-axis. And I'm going to do the frequency in decades. So 0, 1, 2, 3, 4. And this is frequency in decades. So all that means is that these values are really 10 to whatever number this is. So this is just 1, this is 10, this is 100, this is 1,000, this is 10,000, etc., etc. You can go back down negative, and then you get 0.1, 0.001, etc., etc. So let's call this 40, call this 20, 0, negative 20, negative 40. So when omega equals 1, this s, the magnitude of this s is just 1. 1 we say is less than 5, so we can just ignore this. 1 is way less than 500, so we can ignore this s. So this whole value here is just our k, because it's 5 times 10 to the 4th times 1 divided by 5 divided by 500. So k in decibels is about 26 decibels. So at 0, we're going to have a value that's about 26 decibels. And because we have the 0 at the origin, we know that the line from the origin to the first pole is going to have a slope of 20 decibels per decade. So we draw a line through here. It's about 20 decibels per decade, which looks like that. Our first pole is at 5. 5 is about 0.69 on the decade scale. The poles lowered the slope by negative 20 decibels per decade, but our slope's already at 20 decibels per decade, so that means we're just going to be constant here until our second pole, which is at 500, which is about 2.69. And once we reach our second pole, we're going to lower it by negative 20 decibels per decade again. And that means that we get a slope like this. So this slope's at 20 decibels per decade. This is at 0, and this is at negative 20 decibels per decade. Now, I just like to find the point at 0 because that's an easy one to find because you just have to plug in 1 for all these values, and then you can make assumptions on these bottom ones. You can actually find the slope, the value at any point, and then go based off that, but I like to find the ones to the left of all the poles and all the zeros except 0 at origin. So like, say instead of finding it at the origin, we wanted to find it at, say, 50. Then we would put in 50 here. 50 is significantly bigger than 5, so we can just ignore 5. 50 is significantly less than 500, so we can ignore the 50 here. So then we have and 50 up here. So this 50 cancels with this 50. And we just have 5 times 10 to the 4th divided by 500. And so that just gives us with 100, which is 40 decibels, which, as you can see, at our point that's 50 right here, we're at 40 decibels. So that confirms that this is at the correct point here. But so if you wanted to do it this way, you just find this point and you go forward, and then you go negative 20 decibels per decade, and you go backwards until you hit a pole. And because you're going backwards, that would make it go down instead of going. What I'm saying is that this form of line, like the upward slope constant and downward slope, is always going to be the same. Where these actual values are, you can determine at any point and tie it all together, because it's always going to have this form of slope. Now we're going to do the frequency. For the frequency, just going to do 90, 0, negative 90, go 0, go 1, and 2, and 3, and 4. And this is in decade, and this is in degrees on this side. This is the phase of each of. Strictly speaking, this should be j omega, not s here. But so because we have a 0 at the origin, that means we come in at 90 degrees. Our first pole is at 5, which is right here. We're going to go 1 decade less than 5, which is about right here. So that means at this point, we're going to start going down by 45 degrees per decade. And then we're going to go to 1 point to the right of 5, which is about right here. And a pole contributes negative 90 degrees of phase. So you see, we go from 90 to 0 because the pole gives us negative 90 degrees of phase. This is just an approximation, the 45 degrees per decade. It's when you actually calculate it out, these are all going to be curved lines. They're not going to be at this exact slope. But this is a good for approximation, like where we should be. And then we're going to have the negative 90 degrees from the 500, which is around right here. 1 back from 500 is exactly where we ended. 1 in front of 500 is right here. So go another negative 90. Have the exact same slope. So you see you come in at 90 from the 0 at the origin, and then you have 2 poles contributing negative 90 degrees, and that gets us down to negative 90 from 90. And this is at 45 degrees per decade. And there you have your Bode plots. All you need to find is the k, which is the constant, the location of the zeros, and the location of the poles. And you can determine everything else from that. Just remember the 20 dBs per decade and plus or minus 90 degrees for each polar zero. And the approximation is 45 degrees per decade. So you do it out over 2 decades, centered around where the pole or the zero is. So for example 2, we're going to have a circuit with V in this is just an inverting amplifier. And we're going to calculate V out over VI. So to do this, we want this current, call it I in. We know that this is an ideal op amp, so the voltage at the negative node is going to be the same as the voltage at the positive node, which is just 0. So that means the current over here, we remember V equals I. We're going to call this Z instead of R, it's just impedance. So therefore, equals VI 1 over Z2. And Z2 is just going to be R2 plus 1 over SC2. And this is just the form of the capacitor, the impedance of the capacitor. So simplify, putting this all in one form, we'll get R2 C2 S plus 1 over SC2. So we'll get I in equals VI SC2 over 1 plus S R2 C2. Now to find this output voltage, the current through the input is going to be the same across this because none of it's going through the op amp across this branch here. So we need to find Z1 because negative V out here, because the current's flowing from 0 to V out, so therefore V out would have to be negative, equals I in times Z1. Z1 is going to be, well, so these are in parallel, so we can do it, say 1 over Z1 equals 1 over R1 plus SC1, which is equal to 1 plus SC1 R1 all over R1. So then we get negative V out equals I in R1 over 1 plus SC1 R1. Plug in I in here, and you get V in SC2 R1 all over 1 plus S R2C2 1 plus S C1 R1. And then that gives us V out over V in is equal to negative R1 C2 S over 1 plus S R2 C2 1 plus S R1 C1. So here's our transfer function. So we're going to do the exact same thing we did in example 1. We're going to find K, which is just R1 C2, which is equal to 10 to the negative 4th. That's just because these are 1, so R1 C2 divided by 1 is R1 C2. We have a 0 at the origin. We have a pole at 1 over R2 C2 and 1 over R1 C1, which, when we calculate them out, is 10 to the 6th and 10 to the 4th. So now let's do the Bode plots of these. So we have K equals 10 to the negative 4th, 0 at 0, pole at 10 to the 4th, 10 to the 6th. Negative 20, negative 40, negative 60, negative 80. So this is V out over V in, J omega, magnitude in decibels. And this is frequency in decades. So 10 to the negative 4th is the same as negative 80 decibels at 0 decades. We know we're going to go up 20 decibels per decade until we hit our first pole at 4. So we go up 1, 2, 3, 4. This should be a straight line, but my scale is a little bit off. Then this pole evens us out. And we know we're going up 20 decibels per decade because we have a 0 at the origin. Then the pole at the 4th decade evens us out until we hit the pole at the 6th decade. And then we start going down 20 decibels per decade. So this is 20 decibels per decade. This is negative 20 decibels per decade. So you see we have the same slope as the last one, it's different poles and different constant. And now we got to do the frequency for this. So start at 2, 3, 4, 5, 6, 7, 8. This is in decades. This is V naught, V in, J omega, in degrees. Start at negative 90 degrees, negative 180 degrees, negative 270 degrees. Okay, so now we got to figure out where we start. So we have the 0 at the origin, which gives us 90 degrees. However, we also have this negative here, which contributes either plus or minus 180 degrees. So I chose to do negative 180 degrees just because that keeps it close to 0. If you add 180, it's fine. It just goes up to 270. It's the exact same point because any point that's 360 degrees from another point is equivalent. So you come in at negative 90 until you reach 1 decade below our pole, which is at 3. Then you start going down at 45 degrees per decade over 2 decades. That gets us to negative 180. And then you go down. Then our next pole's at 6, 1 degree less than that's 5, which is right where we end. So you go down another negative 45 degrees per decade over 2 decades till we reach 7. So this is 45 degrees per decade. So you notice that the slope is the exact same as from example 1. It's just where it is on the scale is different. And that's because of the negative sign, which changes it by 180 degrees. And that's all there is to drawing Bode plots. Later you'll be trying to figure out stability criteria and how to make your system stable from these Bode plots. So you might be looking at gain margin and phase margin. And that's one of the reasons why it's helpful to keep this in the lower quadrant, because you're usually looking at relative to negative 180 degrees when you're talking about stability. It's the same thing if it's in the top, but you usually talk about it in regards to negative 180. So that's why I like to start at negative 90 instead of 270. And that's all for today.